there, this is Professor Shannon Gracey. Today we're going to be talking about exponential functions, which is section 5.4 in the Larson and Edwards Calculus book. So this is a big section. We've squeezed in differentiation and integration into one happy section. So just make sure that you keep track of everything the best you can. All right, so here we go. Let's start out by warming it on up. So we're going to differentiate the following functions with respect to x. Remember, you are allowed to log both sides of an equation in order to be able to integrate it, because the general power rule, if you recall, is not for unknown values. It's not for variables. It's only for rational numbers. All right, so give it a try and then see how you did. On your mark, get set, go! You can do it. Okay, let's see how you did. Well, as I hinted at, with this guy, what we're going to want to do is we're going to want to natural log both sides of the equation. So we'll have natural log at y is equal to natural log at x raised to the 5x. So rewriting, we will have natural log at y is equal to 5x times natural log at x. So now differentiating both sides with respect to x, we will have an implicit differentiation on the left side, right? So we'll basically have dy dx over what you originally had, which is y, or y prime over y, and that's going to be equal to, look at what we have now, starts with a p. Awesome, you've got a product. So you're going to be differentiating the first guy with respect to x, and you get 5, and then you multiply that by that second factor, right? And then the second part, we will be differentiating natural log at x, and we'll get 1 over x. All right? So moving right along, we will have dy dx. Now if I multiply both sides by y, right? So multiplying both sides by y, I will have dy dx is equal to, I'll bring the y to the front over here, and then we're going to have 5 times natural log at x plus 5. But what was y in the first place? Beautiful. Y was x raised to the 5x. So dy dx will be equal to x raised to the 5x times the quantity. I'm just going to commute the terms here. 5 plus natural log at x. And we're all done. How'd you do? Awesome. Remember the power rule, right? d dx of some function if u is a function of x, right, to the n, using the power rule on that, you would get n times u to the n minus 1 times du dx, right? And n is an element of the rational numbers. The rational numbers, I think, are a q. So I'll just write it out. So n belongs to the rational numbers. So a rational number is any number that can be made into the form of a fraction, right, in integer over integer format. So we can't use that rule when you've got a 5x in there, right, because of that x. Okay? All right, so here we go. Next step. Let's see how you did. Now this time we don't have to natural log both sides, right? Because it's already a natural log. And really, there's an easy way and a hard way to do this problem. If you use properties of logs before you integrate, do you see you'll get cosine at 2x times natural log at e. But what is natural log at e? Beautiful, 1. So you just get cosine at 2x. And if you differentiate with respect to x on both sides, you'll have f prime at x is equal to, perfect, negative 2 times sine at 2x from our old rules. All right? Okay, so next up we have the natural exponential function. All right, so for this guy, the natural exponential function, all right, the inverse of the natural logarithmic function, f of x equals natural log at x, is called the natural exponential function. And this guy is denoted by, call it g of x is equal to e to the x. All right, so basically g of x is also equal to f inverse at x. We have f evaluated at g at x is equal to x, which is equal to g evaluated at f at x. Okay, so the inverse relationship between the natural log function and the natural exponential function can be summarized as follows. So y equal to natural log at x if and only if e to the y is equal to x. Okay? So let's see what we've got going on. Let's look at this first example. We're going to practice solving equations, right? So why don't you, again, give these a try, see how you do. We'll be looking for the exact result, and then we'll look for the approximation to 3 decimal places, okay? All right, so e raised to the natural log at 6x, basically you have the natural exponential function being evaluated at the natural log function. So this is just going to be what's inside that log, 6x, and that's equal to 20. So dividing both sides by 6, you would end up with, what, 10 thirds, right? So 10 thirds is the exact result, right? And then approximate result would be, all right, so what was it, 10 thirds? And that would be 3.333. Okay, moving along. Okay, so next up we've got 5,000 over 1 quantity 1 plus e to the 2x is equal to 2. So if we clear out those fractions, right, we'd end up with 2 oops, there we go, 2 times 1 plus e to the 2x is equal to 5,000. So what we want to do with this is isolate the exponential term. So we have 1 plus e to the 2x is equal to 2,500. Taking away 1, we have e to the 2x is equal to 2499. And so now we need to, what do you think we need to do? We need to get that power as a factor, right? So to do that, we can natural log both sides, and we end up with perfect. 2x on the left side is equal to natural log at 2,499. And dividing by 2, we get x is equal to, I'll just call it 1/2 times natural log at 2499. And with this one, I guess an good exact one would be using properties of logs. Do you see this would be natural log at the square root of 2499? And let's see. Well, we can simplify the radical a bit. I know 3 divides it, but you know, that's just kind of going above and beyond. Let's go ahead and call that one the exact, okay? And the approximate, let's see what we would get. We'll just do that first version. So 0.5 is 1/2 times, and then we're doing the natural log at 2499. Enter, and we get approximately 3.9118, I think. Yes. Well, 3 spaces would be 3.912. Okay, so exact approximate and we're good to go. Okay, so let's see what we have going on here. Next one, natural log at 8x is 3. So what do you think? Good, we can, this is true if and only if. What's the base of the natural log? Good, it's e. So the e grows up tall. A logarithm is an exponent, so the 3 goes here, and that's equal to 8x, right? So x will equal to e cubed over 8. That's our exact result. X would be approximately 2.511. Right. So exact. And approximate. Alrighty, and then part F. These I think are kind of groovy. It's actually something that is quadratic in form, right? So you want to get used to being able to see that e to the 2x is equivalent to e to the x, the quantity squared. Because remember, if you raise a power to a power, you multiply. So we have really 1 times that, right, minus 2 times e to the x minus 8. So this guy ends up being quadratic in form. So you can either let u equal e to the x if you need to, or you can just factor directly. I think this guy will factor. So you would end up with e to the x and e to the x. And then let's see, we're going to have 2 and 4. The 4 will be negative, the 2 will be positive. And let's see, does that work out okay? Yes, it does. Perfect. So now we end up with e to the x plus 2 is 0, or e to the x minus 4 is 0. So e to the x equals negative 2, or e to the x equals positive 4. So what do you think? Good. This guy is extraneous because why? Good. The range of e to the x is from 0 non-inclusive to infinity, so you can't have a negative result, so this guy is out. But this guy's fine, and what do you think we should do? Perfect. Natural log both sides. We end up getting x is equal to natural log of 4, so that's your exact. When we approximate, we would get 1 point, again, I forgot to see where it went to, 1.386. All right, so exact, natural log of 4, approximate 1.386. All right, so now that you're remembering a little bit, hopefully, about the natural exponential equations, let's look at graphing f at x is equal to 2e to the x minus 1 without using our calculator. So let's just kind of scope it out and see what we have going on. So here, let's go ahead and put a grid in there. So with this one, you know, the idea is that you get a few of the points that you know, and then you'll have you can do the general shape, and then figure out what's going to happen with the translations. So this would be x, and this would be f at x, and let's just do 5 and negative 5 for the x-axis, and then 10 and negative 10 for the function axis. If we kind of do sort of a little ghost graph of, you know, what f of x equals e to the x, or some g of x is e to the x, right? So g at x is e to the x. We know that that is going to look something along the lines of, when you have a 0 input, you would have an output of 1, right? When you have an input of 1, you'd just be at E, so you'd be at about 2.7-ish. So we'd have something along these lines, right? Okay. So now what we need to do is we need to shift it 1 to the right, and then double each output. So we'll do our graph in blue, right? So our graph f of x is going to be 2 times e raised to the x minus 1. So everything will be shifted to the right by 1. So I'm going to go from this first order pair at 0, 1 from the gray graph, shift it over to the right 1, okay? And then we are going to double that output. So we'd be up at 3, okay? Now, again, going from this ordered pair, scooting it over 1, and then doubling it, we'd be at about, oh, I don't know, 5.4-ish. So we'd be at, okay, so what's happening with this guy is everything is going to just, it's going to shift over, and then it's going to expand a lot more quickly. All right, so yeah, it'd be about like that. And then of course you can check it, but it had just a couple of shifts. Something like that using the translations. So long story short, shift 1 to the right from g of x is e to the x, and then double. Okay, so here we go. The derivative of the natural exponential function. So here with this one, all right, the way we're going to show this, it's kind of groovy, since we know that if you have y equal to e to the x, right? That's true. IFF means if and only if. We have what? Natural log at what? Y is equal to x. Good so far? So here, to find the derivative of the natural exponential function, what we can do is we can differentiate that second one, right? So we've got this natural log at y is equal to x, and if we differentiate both sides with respect to x, what's going to happen? We're going to get beautiful dy dx, dy dx over y, that's the derivative of the left side, is equal to 1. So isolating our dy dx, we would have dy dx is equal to y. But what was y? E to the x. So isn't that awesome? What we found was the derivative with respect to x of e to the x equals e to the x. Isn't that awesome? Right? Okay, so now let's look at it. If you had, so if you have something along the lines where u is some function at x, right? So let's do it the same way, right? So if you have y is equal to e to the u, what does that mean? That's true if and only if natural to u. So then differentiating both sides with respect to x, we'll get perfect dy dx over y is equal to u prime, right? So then dy dx is equal to u prime times y. Actually, we'll do it as y times u prime. And what was y? Y was e to the u. So dy dx is going to equal to e to the u times u prime, or du dx. So we found that d dx of e to the x is equal to e to the x. d dx of e to the u is equal to e to the u times u prime, or e to the u times du dx, however you want to do that. So basically, you rewrite the exponential portion or factor exactly as it is, and then you multiply that by the derivative of the power. Okay? Alrighty, so let's do it. We've got d dx. Sorry, these should have started at a. So d dx of y equal to d dx of e raised to the 5 minus x cubed. So on the left, we'll get dy dx. And then on the right, what's going to happen? You rewrite the exponential exactly as it was. And then you multiply by d dx of the power, which is 5 minus x cubed. So dy dx will be, so the derivative of 5 minus x cubed is going to be, 3x squared, I'm going to put that first, then times e raised to the 5 minus x cubed. And we're done. Okay? Alright, so that was our A. This should have been B. Alright. So again, you're going to need to use all of your, strategies that you learned in Chapter 2. But it's just something that, you just have a couple new formulas, right? So here, differentiating both sides with respect to x, we have, f prime at x is equal to, so we have a product rule. So the derivative with respect to x of x is 1 times e to the 3x plus x times, rewrite the e to the 3x exactly as it was, right? Let me do. And then you're going to multiply by the derivative with respect to x of that power, right? 3x. Okay, so far? So what's going to happen is we will get f prime at x is equal to e to the 3x plus x times e to the 3x times 3. Cleaning it up a bit, we'll get f prime at x is equal to e to the 3x times 1 plus 3 times x. And just so you can match stuff up, let's see what we had. So this whole thing here, which resulted in, this portion here, all of that was d dx of our e to the 3x was all in the yellow. Okay? And the rest of it was utilizing the power rule and then simplifying. Okay, so our next one, what do we have going on here? Woohoo! Natural logs and natural exponentials. What a surprise. What do you think we should do first? Good. I think, as you said, we should use properties of logs to rewrite this guy. So this will be the natural log at quantity 1 plus e to the x minus the natural log at quantity 1 minus e to the x. Now, differentiating with respect to x, we'll have, good, y prime is equal to, perfect, so we're going to have, just to remind you, d dx of our 1 plus e to the x, and that's going to be over 1 plus e to the x. So your u in this case is 1 plus e to the x. And then the next one we'll have minus d dx of 1 minus e to the x over 1 minus e to the x. Good so far? Awesome. Alrighty, so we will have y prime is equal to, so that derivative in both those numerators is going to be e to the x, right? Because you'd get in the first one 0 plus e to the x, and that's going to be over 1 plus e to the x minus negative e to the x, right, over 1 minus e to the x. All right, so getting a common denominator of 1 plus e to the x times 1 minus e to the x. In the numerator, we'll have e to the x times 1 minus e to the x plus e to the x times 1 plus e to the x. So we will have y prime is equal to e to the x minus e to the 2x plus e to the x plus e to the 2x over 1 plus e to the x times 1 minus e to the x. So y prime equals, so we'll have 2e to the x's, and the e to the 2x's zero out, and that's going to be over, I'll just keep it in factored form, 1 plus e to the x times 1 minus e to the x. And we're done. All right? Perfect. Okay, so now this one is what? No, part D. So for this guy, differentiating both sides with respect to x, we will have y prime equals, I'm going to pull out that 1/2, right? And then we will have the derivative with respect to, I'll just write it out, so we'll have d dx of e to the x, and then minus d dx of e to the negative x. So we'll have y prime equals 1/2 times, good, e to the x, and then minus e to the negative x times -1. So this here is those correspond, and this here is equivalent to this. So cleaning it up, what will we have? We'll have y prime is equal to 1/2 times e to the x plus e to the negative x. And it depends. Yeah, usually you'll give instructions to leave, to write things in the form of, a single rational expression with no negative exponents. So we'll do a little work on this, okay? So we'll have 1/2 times e to the x over 1, right? And then plus 1 over e to the x. So getting a common denominator, we'll have e to the x is our common denominator. The second part doesn't need anything. The first part, that e to the x, needs another e to the x to balance it out. So at the end of the day, we'll get e to the 2x, right, plus 1 over 2e to the x. Alrighty? And then we're all set. Okay, so now this one, we're going to need to implicitly differentiate. So evaluating the derivative with respect to x of both sides, what's going to happen is we'll get 3 of these derivatives going through on the left, and then on the right we'll get a result of 0 because it's a constant. So this first one will be d dx of xy, and then plus d dx of x squared, and then minus d dx of y squared, and that's all going to equal to 0. Now, so we just make sure you're just being careful, following all the steps. So here we go. The derivative with respect to x of e to the xy is going to be e to the xy, right, times the derivative with respect to x of the power x times y. And then the next one is just explicit. It's just going to be 2x. And then this guy you had practice on before, right? You're going to get 2 times your something to the 1 times the derivative with respect to x of your something. And that's all still equal to 0. Okay, so moving along, we're going to have e to the xy. The derivative with respect to x of the product x times y is going to be, good, 1 times y plus x times, perfect, dy dx. And then we have our plus 2x, and then minus 2y times dy dx is all equal to 0. Now, moving right along, we will have y e to the x y plus x e to the xy times dy dx plus 2x minus 2y times dy dx is equal to 0. So now we need to group the terms that have dy dx, right? So we'll be able to factor out a dy dx, and we'll be left with xe to the xy minus 2y. And then if we move the other terms over that don't have a factor of dy dx, we will have negative 2x plus ye to the xy. And just so you can keep track of which derivatives match up to each other, this whole thing, right, ended up being this. Of course, this one should have been relatively easy for you. And this guy here was all of this. Okay? And then over here, the d dx of x times y was this portion of it. All right. So now, moving back, we will have dy dx is equal to negative 2x plus ye to the xy divided by xe to the xy minus 2y. Now, if you had opted to bring that negative into the bottom, the denominator, you might have something slightly different. The prettiest way to write this would have been this way, where you brought that negative into the denominator, you distributed it through, and you would have ended up with 2y minus xe to the xy. So both of those are fine. Groovy? All right. Now, what does this one look like? Which part was that? That was part E. So we were on part E. Now this will be part F. Okay, so this one, what's that theorem again? Perfect. The second fundamental theorem of calculus. So on the left, we're going to get capital F prime at x. But notice that you've got a function of x, right, going on. So what we're going to need to do is we're going to need to, this can be written as if u is equal to e to the 2x, right, du dx would end up being, beautiful, e to the 2x times 2, which would give us du dx is equal to 2e to the 2x, right? So what we'll have is du of the integral from 0 to u of natural log at t plus 1 dt, and all of this is going to be multiplied by du dx. So if you'll see, you still have d dx, because technically those du's could cancel out. So then capital F prime of x by the second fundamental theorem of calculus is natural log at u plus 1, and then times du dx, right? So then capital F prime of x will be natural log at u was e to the 2x, and then du dx was times 2e to the 2x. And then I guess we could clean it up a little. Capital F prime at x will be 2e to the 2x times natural log at e to the 2x plus 1. Okay? All right. Now we will apply this and find an equation of the tangent line of the function at the point 1, 1. Okay? So it's really going to be the equation of the tangent line at this point. So what do we need to do? We need to find the slope, right? At 1, 1. So with this one, the nice thing is we're not going to have to simplify because we have an ordered pair to plug in. So we're going to be differentiating 1 plus natural log at x times y on the left side, and then on the right side we'll be differentiating e raised to the x minus y. And this is all with respect to x. So this derivative is going to be d dx of the product xy over 1 plus natural log at xy. You could have split those if you wanted to. Either way, it's probably a similar amount of work. So this is going to end up being e to the x minus y multiplied by d dx of x minus y. Okay, so now we will have, this one's going to end up being, we found it in the last problem, so 1y plus x times dy dx over 1 plus natural log at xy equals e to the x minus y times 1 minus dy dx. Okay, so now we have everything, and remember we want to do this at the ordered pair 1, 1, right? So this will be e to the 1 minus 1. Actually, you know what? I'm sorry, I'm being sloppy. Let's just do it like this. So we'll say at the ordered pair 1, 1, what will we have? So we'll have 1 plus 1 times dy dx over 1 plus natural log at 1 times 1 equals e raised to the 1 minus 1 times 1 minus dy dx. And then we need to isolate our dy dx. So natural log at, well, 1 times 1 is 1. Natural log at 1 is 0, right? So this is going to give us 1 plus dy dx over 1 is equal to e to the 0 times 1 minus dy dx. E to the 0 is just 1. So we will have 1 plus dy dx on the left is equal to 1 minus dy dx on the right. So we'll be adding a dy dx to both sides and subtracting 1. So we'll get on the left 2 of those dy dx's is equal to 0. Well, that's a bummer after all that work, huh? So dy dx is 0. So what happens when you have a slope of 0? Good, it means you have a horizontal line, so y equals 1. It's just going to go the horizontal line y equal to 1 will be the equation of the line, the tangent line at that point. Okay? Okay, next up, another example here. I was trying to get sort of a review of a lot of stuff that we've done. So finding the extrema and points of inflection of the function g of x is equal to 1 over root 2 pi times e to the negative x minus 3, quantity x minus 3 squared over 2. Okay? So this is actually a probability density function in statistics. So it's actually our bell curve. So with a mean of what? 3, I think, a mean of 3. So anyway, what we're going to have is we're going to have extrema and points of inflection. We need the first derivative, we need the second derivative, and we need to find a whole bunch of stuff, right? So first off, we'll say relative extrema. Actually, I'm not sure which one I'm going to use, so let's just say we want to find critical numbers for g. So remember, you differentiate and set the derivative equal to 0 to find that. So here, what we'll do is we'll have d dx of each side. So this was d dx of g of x is equal to d dx of 1 over root 2 pi times e to the negative quantity x minus 3 squared all over 2. So on the left side, we're going to get g prime of x. On the right side, we can factor out the 1 over square root of 2 pi. You rewrite this exponential exactly as it was. And now what we need to find is the derivative with respect to x of that power, which is, I'm going to write it as negative 1/2 times quantity x minus 3 squared. Good so far? Okay, so g prime of x will be 1 over root 2 pi times, actually, you know what, just to make it nicer, I'm going to write e raised to the negative x minus 3 quantity squared over 2. And then the derivative of this guy is going to be what? Negative 1, right, times x minus 3 to the 1 times 1, using the chain rule. So g prime at x is equal to x plus 3. We'll end up with 3 minus x. I'm going to write it like this. We'll have 1 over root 2 pi times 3 minus x times e raised to the negative x minus 3 squared all over 2. Okay, so we need to find the zeros of this. So basically, you know, we're going to end up, do you see that we're going to end up having to, I want to highlight this here. We're going to, on the second derivative, we're going to use this again, right? So I'm going to put let's put a note that this right here, all of this right here, is the derivative with respect to x. You know, it's all what we found. Okay, and the reason I'm highlighting it is because in that second derivative, I think we come across it again. Okay, so now let's find the zeros of this guy. So 0 equals all of this. So 1 over root 2 pi times 3 minus x times e to the negative x minus 3 quantity squared over 2. Now, the exponential will never be 0. So it actually ends up being quite simple because he just need to set 3 minus x equal to 0 for that whole thing to zero out. So we would end up getting x is 3. Okay? So our critical number, our c, is 3. Now, since we have g prime of x right here, let's go ahead and find g double prime of x. So g prime of x, I'll rewrite it, 1 over root 2 pi, actually write it as, now I'll write it like this, 1 over root 2 pi, I'm going to write it like this, e to the negative x minus 3 squared, that over 2, times 3 minus x. So now when we differentiate with respect to x on both sides, we end up with a product on the left side. And we already have the yellow derivative, right, that we had found. For that first part of it is g, right? Remember, g was that. So g prime is going to be, we're going to know what d dx of that one is. So let's do it. We'll have g double prime at x is equal to, we're going to have this product. So we'll have d dx of all of this, 1 over root 2 pi times e to the negative x minus 3 quantity squared over 2. And then that's going to be multiplied to 3 minus x, and then plus 1 over root 2 pi times e to the negative quantity x minus 3 squared all over 2 times the derivative with respect to x of 3 minus x. Just using the product rule, you know, I know it's a little mean. Now, we already have the derivative of 1 over root 2 pi e to the negative x squared. It's this yellow stuff, right, that we highlighted, okay? So I'm going to rewrite that. So this first one, we'll have g double prime at x is equal to 3 minus x over root 2 pi times e to the negative x minus 3 squared over 2. I got that earlier, and so we don't need to go through all that work again. We got that earlier. Okay? And then we'll be multiplying this to 3 minus x, and then the derivative with respect to x of 3 minus x is negative 1. So it'll just flip the sign. So then we'll have minus 1 over root 2 pi times e to the negative quantity x minus 3 squared over 2. Okay, so g double prime at x will be, we can factor out 1 over root 2 pi times e to the negative x minus 3 quantity squared over 2, and we'll be left with 3 minus x, the quantity squared, minus 1. So again, to get the zeros, what we'll do is we will equate the part that can zero out equal to 0. And so when we solve, we'll have 3 minus x, the quantity squared, is equal to 1. And then we can square root both sides. You get a plus or minus, of course. And we're going to get 3 minus x is plus or minus 1. So if for x equal to positive 1, what would that be? X would have to be 2, right? And for it to equal to negative 1, x would have to be 4. Okay? So now, unfortunately, we've run out of space. Just to remind you, g prime at x was equal to 3 minus x over root 2 pi times e to the negative quantity x minus 3 squared all over 2. G double prime at x was equal to, let's see, we were factored that out, right? So we had 1 over root 2 pi times e to the negative x minus 3 quantity squared over 2 times 3 minus x squared minus 1. And our zeros from the first derivative, that one was so long ago, 3. And critical numbers from the second one were okay, so the c was equal to 3 for this one, and the zeros for this guy were 2 and 4. I'll keep them in terms of x. X is 2 and 4. All right, so now this is what we're going to do. For relative extrema, I'm just going to use the second derivative test, which said that we want to take that if g double prime at c is less than 0, that implies a relative, what? You remember? So you're curving downward, so it'd be a relative max. And g double prime at c greater than 0 would imply a relative min, because you're curving upward where the extrema is. So hopefully we won't get that it's equal to 0, because then we'd have to just run the first derivative test anyway. Okay, so now let's do it. G double prime at 3 is equal to 1 over root 2 pi times e to the negative 3 minus 3 squared over 2 times 3 minus 3 squared minus 1. So, let's see what we get. G double prime at 3 is equal to, the e to the 0, that's all just going to be 1. So we'll end up with 1 over root 2 pi times 1. 3 minus 3 is 0, so we'd get times negative 1. So this is less than 0. So it implies relative max. Good so far? Now, let's go ahead and find the rest of the information for the relative extremum. So G at 3 is going to be 1 over root 2 pi times e to the negative 3 minus 3 squared over 2. So, what's that going to be? Good. That's going to end up being 1 over root 2 pi. Good so far? So, we have an ordered pair at 3 comma 1 over root 2 pi. All right, so we'll put all our conclusions at the end. We got to find out if there's any points of inflection, right? So we're going to make a number line divided up by the zeros of the derivative, right? So we've got 2 and 4. So we got to test minus infinity to 2, 2 to 4, and then 4 to infinity. So G double prime at, how about 0? That'll be easy. Is going to be 1 over root 2 pi e to the negative 0 minus 3 squared over 2, and then 3 minus 0 squared minus 1. So G double prime at 0 is going to be negative. Okay, so we already have G double prime at 3, and G double prime at 3 oh no, you know what? I'm sorry. I'm spacing out here. This is going to be positive, right? This is going to be positive. So those two positive factors mean that we'll have a positive. So G double prime at 0 is greater than 0. G double prime, so we're choosing to test 0, 3, and 5. So G double prime at 3 we already have from over there, from the second derivative test, and we know that that's less than 0. And then G double prime at 5 is going to be 1 over root 2 pi e to the negative 5 minus 3 squared over 2 times 3 minus 5, the quantity squared, minus 1. So that's going to be a positive, and this is going to be a positive. So G double prime at 5 will be greater than 0. Okay. And so now there is a change in concavity at both 2 and 4. So we've got to find the outputs, right? So let's so basically what we have is we got to find G at 2. So that's 1 over root 2 pi times e raised to the negative 2 minus 3 squared, and then times 3 minus 2, the quantity squared, minus 1. So G at 2 will be, this is all over 2. So that would be, this is going to be, all of this would be what? 0, right? Is that right? 1 minus 1 is 0, which would make everything 0. So G at 2 is 0. G at 5 is going to be, no, we need 4, I'm sorry. G at 4 is going to be 1 over root 2 pi e to the negative 4 minus 3 quantity squared over 2 times 3 minus 4, the quantity squared, minus 1. So do you see that's going to 0 out again, which will make everything 0 out? So G at 4 is also 0. So now let's put our conclusions. Finally, all right, so conclusions. All right, so there is a relative maximum at, what was our ordered pair? I think it was 3, 1 over root 2 pi. And the 2 points of inflection occur at 2, 0, and 4, 0. And then let's make sure we answered everything. We needed to find, yes, the extrema and points of inflection. So we're good to go. Yay, yay. Okay, so next up, we go here. So since the derivative of the natural logarithmic function is itself, then the antiderivative of it also is itself. So this would be e to the x plus c, and this would be e to the u plus c. So now practicing, it just takes practice, practice, practice. Right? So again, here we go. This one, what do you think? Maybe our u should be what's in the power. So then du dx would be equal to 12, and then dx would be du over 12. So we would have, this is equivalent to e to the u, and then times du over 12. So n for dx was du over 12, and then u was the power. So this is going to be 1/12 times the integral of e to the u du, and that will give us 1/12 e to the u plus c. Back substituting, we'll have 1/12 e raised to the 12x plus c. Okay, awesome. Next up, we've got this guy. So again, what do you think? Take a look at it. What would your u substitution be? Beautiful. Again, it's in that power. So then du dx is equal to negative 5x to the 4th, And then isolating dx, we'll have du over negative 5x to the fourth. Alrighty, so now we will have the integral of x to the fourth times e to the u times du over negative 5x to the fourth. Okay, so fortunately the x to the fourth divides out completely, and so this is going to be negative 1/5 times the integral of e to the u du, which gives us negative 1/5 times e to the u plus c, and we'll have negative 1/5 times e raised to the 1 minus x to the fifth plus c. How's it going so far? Good. Okay, so next up we've got this one, and so here, you know, there's a couple ways one could go about this. Remember, you do have the ability to use long division here. But, you know, I think it might just it might look more complicated that way. We'll just do this as a u sub. So remember, we can rewrite this guy as the integral of e to the 2x times 1 plus e to the 2x raised to the negative 1 dx. So the more complicated part would be the 1 plus e to the 2x, because that's being raised to the negative 1 power. So differentiating with respect to x, we're going to have, good, 2e to the 2x. So then isolating dx, we'll have du over 2e to the 2x. So plugging in what we've done, we'll have the integral of e to the 2x times u to the minus 1, and then times du over 2e to the 2x. So the dx is from here, and then our u was in here, and the e to the 2x's divide out, so we'll end up with 1/2 times the integral of u to the minus 1 du. So what will we get for that result? Perfect. That's going to be 1/2 natural log at absolute u plus c, which is 1/2 times natural log absolute 1 plus e to the 2x plus c. Now if you look at 1 plus e to the 2x, what you'll notice is that it's always positive. The natural exponential function is always positive, and when you increase it by 1, it's still positive. So cleaning this up, using the power rule for logs as well, you don't need absolute value bars, and it'll be equivalent to the natural log of the square root of 1 plus e to the 2x plus c. Okay? All right. Okay, our next problem, what do you think we might want to do? We've got a monomial in the denominator, so what, starts with A, not a bad word. Good, algebra, right? So let's rewrite this guy. We're going to divide through by e to the 1x, right? So that'll give us e to the x plus 2 plus e to the negative x dx. So now the first part doesn't need a u sub, right? E to the x plus 2 we'll be able to, with respect to x, we'll be able to integrate. I'm going to separate this guy because if you're using u substitution, you'd need one on just that part. So to set that up, we'd have u is negative x, du dx is negative 1, so dx is negative du. Okay, so we're going to get e to the x plus 2x as the result of the first integral, and then plus the integral of e to the u times negative du. So this guy was the one that needed the little u substitution. Okay, so we'll have e to the x plus 2x minus the integral of e to the u du. So this will be e to the x plus 2x minus e to the u plus c, and we'll have e to the x plus 2x minus e to the negative x plus c. And you're all done. So there's a lot of different strategies a person uses with an exponential function. Okay, what about this guy? Again, let's try what's in the power. Okay, so then dx would be du over 2 times secant squared at 2x. So I think this will work out nicely. So rewriting our integral, we'll have e to the u times secant squared at 2x, and then we'll have times du over 2 times secant squared at 2x. Okay. Okay. So moving right along, the secant squared at 2x's divide out. So we will have 1/2 times the integral of e to the u du, which will give us 1/2 e to the u plus c, and we'll have 1/2 e to the tangent at 2x plus c. Whew. All right. Now we've got some definite integrals going on. So remember, you also want to change the limits of integration as well. So here, if we rewrite this guy, we would have the integral from 0 to 1 of e to the x times 5 minus e to the x to the negative 1 dx. So I'm thinking our u sub should be beautiful. 5 minus e to the x du dx is negative e to the negative e to the x, and then isolating dx we'll have du over negative e to the x. Okay, so whoops, what am I forgetting? I needed to change my limits of integration. So u of 0, so the lower one, will be 5 minus e to the 0, which is 4. And u at 1 will be 5 minus e to the 1, which is just 5 minus e. Okay, so putting it all together, we will have the integral from 4 to 5 minus e of e to the x times u to the minus 1, and in for dx we have du over negative e to the x. And this was our U sub. And then we got our limits over here. So again, fortunately, this e to the x divides out. We're going to have everything in terms of u. So this will end up being negative integral from 4 to 5 minus e of u to the minus 1 du, which is negative natural log absolute u, evaluated from u equals 4 to u equals 5 minus e. So we will have, I'll factor out that negative, we'll have natural log absolute 5 minus e minus natural log absolute 4. We don't need the absolute value bars for those, and we can use that quotient rule. So this will give us negative natural log at 5 minus e over 4. And then this is actually natural log at 5 minus e over 4 raised to the negative 1, which would give us the natural log at 4 over 5 minus e. All right, here we go. Now let's solve the differential equation. So if, again, we need to multiply both sides by, oh no, what do we have here? I think I've got a typo. Sorry guys, there's a typo here. I shouldn't have had a dx here. So then what would happen is you'd multiply both sides by dx. This one would divide out. We'd be left with dy is equal to e to the x minus e to the negative x, the quantity squared, dx times dx. Okay, now I can't integrate the right side as it is, so I'm just going to expand that out. I mean, this is the same as e to the x squared minus 2 times e to the x times e to the negative x plus e to the negative x squared. And that's all times dx. So dy will be equal to, we'll have an e to the 2x minus 2, because you'll end up with e to the 0, which is just 1, and then plus e to the negative 2x dx. So now we've got these in a format that we can integrate. So if we integrate both sides, right, on the left side we'll have a result of y, because we were integrating 1 with respect to y. And on the right side, what's going to happen is, what do you think will happen? If you did a u sub, you'd have u is 2x, du dx is 2, right? So do you see that we'll be basically dividing by the coefficient to the x on that linear deal? Or, you know, we could adjust it, split the integrals, adjust them, however it is you need to do it. I'm just going to use pattern recognition, and what's going to happen is we're going to get e to the 2x divided by 2 minus 2x plus e to the negative 2x divided by negative 2 plus our constant of integration. So cleaning it up, we'll have y equals 1/2 e to the 2x minus 2x minus 1/2 e to the negative 2x plus c. Okay, here's an application. The median waiting time in minutes for people waiting for service in a convenience store is given by the solution of this equation. all right? We want to solve it. So let's see what, we would do here, all right? So we've got the integral from 0 to x of 0.3 times e to the negative 0.3 t dt, and integrate. So here, my u would be negative 0.3 t, and du dt would be negative 0.3. So dt is du over negative 0.3. And this is going to be equal to 1/2. Right? So we'll have, and we have to find. So u of x is going to be, let me do the lower limit first. U at 0 is going to be 0, and u at x is going to be negative 0.3x. So now we have everything we need. So we're going to be integrating from 0 to negative 0.3x. We have 0.3 times e to the u, and in for dt, we have du over negative 0.3. That's all equal to 1/2. So this was our substitution here, or our dt was equal to that, and this was what our u was equal to, and we got these limits by evaluating those. Okay, so this is going to give us the 0.3's divide out. So we're going to end up with negative integral from 0 to negative 0.3x of e to the u du equals 1/2. So this will be negative e to the u evaluated from u equals 0 to u equals 0.3x, negative 0.3x, sorry. This is all going to equal to 1/2. So I'm working, both sides of the equation. So we'll have negative e to the 0.3x to the negative 0.3x, and then minus e to the 0. That's all equal to 1/2. So this will give us 1 minus e to the negative 0.3x is equal to 1/2. So e to the negative 0.3x will be equal to, let's see, I'll have a negative, and then this will be a negative 1/2. And so e to the negative 0.3x is equal to positive 1/2. Natural logging both sides, we will have negative 0.3x is equal to natural log of 1 minus natural log of 2. Negative 0.3x is 0 minus natural log 2. So x will be equal to natural log at 2 divided by 0.3. So when we get our approximation, it turns out to be approximately 2.31. So our conclusion would be what? I'll write it up here. Well, I'll just write it in bottom here. So the median, waiting time, for the customers is approximately 2 minutes and it turns out to be 19 seconds when you convert from decimal to minutes and seconds. Okay? All right, wow, that was a long one. Anyway, thank you for your time, and I hope this was helpful. Have a great day. Bye-bye.